So welcome to the Grey Scott Thursday. It's a series of webinars we organize every Thursday at 10, as many of you know, on various HPC topics, such as this one today, which will be presented by Pierre Aubert himself. First, let me give you a little presentation of the organization team. So there is Karim Azoum and I from Terratech, and within the French NCC called CCFR, and with the lab of Annecy, we co-organize the Grey Scott Thursdays and the Grey Scott School, with obviously Pierre Aubert himself, who is a research engineer from the lab, the French Laboratory of Physics and Particles in Annecy. So those Grey Scott Thursdays, there are 17 of them, you'll discover, and they are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is Grey Scott School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. It was created 2 years ago by Pierre himself, with a few people in Annecy, and the French NCC joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. So those satellite sites helped us reach more people by broadcasting the school live in their locations. The summer school had a 2-week program, 1 week on CPU and 1 on GPU, but everybody was free to choose the courses they wanted to attend, thanks to our à la carte option. So we finally trained over 500 people, and everything is available still on replays on our website and YouTube channel if you want. You can access it, but everything is in French. But this year, we are going European. So all will be in English, like this webinar. And you have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also, we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So let me now play the video for you, and then we'll come back with Pierre.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grey Scott School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or à la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, SYCL, Thirst, CUDA, OpenACC, Vulkan, NumPy, Number, QPy, CUNumeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV-Fortran, G-Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Nsight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
So thank you for watching. If you have any question regarding the school, you can ask them in the Q&A section, and Pierre and I will be glad to answer you. Thank you for listening to me. Now it's time to give the floor to Pierre himself.
So hello everybody. So today I will present to you some GPU stuff with C++ 2017 and a bit of 23 also, with CUDA and mainly NVC++, other stuff also, but mainly this. So this is the second part of the C++ webinar. So today we will focus on GPU computing, and the previous one was on CPU computing. And so to start with the same standard, so we have the C++ standard for CPU and GPU. And if you want to compute on a CPU, you can use threading building blocks, for example, parallelization library of Intel. If you want to compute on a GPU, for example, you can use Thrust or CUDA directly. And if you want to do both with more or less work behind it, you can use a bunch of libraries, Kokkos, Alpaca, SYCL, as you already had the webinar from David, OpenCL or OpenSCC. And since C++ 17, we have the compiler, so G++, Clang++, DPC++, also NVC++. They can use directly C++ 17 to call directly TBB. So that's quite a good point. So you still have to link to TBB, so it's not quite straightforward, but you can express your computation without having to think about which thread, which block, how to split the computation. The compiler does it for you, and it's really, really powerful. And since 2020, NVC++ is capable to do that for C++ 17 for the GPU computing. And we can do also some stuff with the DPC++, but I don't have time for that right now. So the point is, with C++ 17, we use directly TBB for the CPU, and for NVC++ and C++ 17, we use directly Thrust to do some CUDA computing under the hood. And the good point is you don't have to worry about the allocation, the data management, the data copy between the host and the device. Everything is handled for you. The number of threads is handled for you also. So everything is quite nice to use. And we will see that in a moment. But first, again, we want to use the GPU, so we have to express parallelism. So, and since we are a lot today, I will take a few minutes to talk about that again, because it's really important. So let's pretend that I have some event to treat. So I have stochastic events, so I have a lot of parallelism for free, so it's nice. I will have a good scalability. But maybe on my GPU, I cannot fit enough event to say I can maybe start one thread per event and use my full GPU at its full potential. So remember, you have to start a lot of threads compared to the number of cores to use your GPU efficiently. So we had at some point to break down the event into, for example, captors, let's say pixels or cells or whatever the captor you have. And maybe it's still not enough in this point. So we will break down the pixel again in slices, waveform, pulses, time response, whatever you call it. Normally you should have something like that at some point. And the question is, okay, but how do I store my tensor? I have a nice tensor, a lot of parallelism to express in it, but how I store it? And to answer this question, we have to ask ourselves, okay, but what do we want to compute with this tensor? And maybe we want to start with a calibration. So let's say I have some voltages as input, and I want to compute the number of photons as an output, or an energy, for example. And let's pretend for the purpose of this slide that this step is independent of the ordering of the tensor. And this part is really important. When I say it's independent, but we have the best performances as possible if we change the order of the axis. Of course, if you kill your performance by changing the axis, you cannot do that. But let's assume we did a little study and to check that we can change the axis and to get the best performances at each time, and it's the case. Normally it's not the case, but let's pretend it's the case for this example. So if it's the case, we do not have to choose for now. So let's have a look to the second step. And the second step might be an integration. So maybe we want to sum the slices together for each pixels with a weighted sum. So maybe we will have some way to do that. So, but basically it's a reduction. And when you heard about reduction, you have to talk about sum, you have to think about backdependency, and you need the reflex to say, okay, I don't want to add this element to this element if they are adjacent to memory, because you will kill your performances because of the backdependency. So naturally, in this configuration, we want the last axis to be this one. So the contiguous data should be on this axis, and then we can sum the rows together to do our computing with the slices. So with this configuration, we can vectorize, and we can GPUify also. And even for the integration, and even also for the calibration, because the calibration does not care. Then naturally, we want to have the second axis, which will be this one, to have rows close together in the memory, to be sure that the prefetch will be efficient. And finally, the first axis will be this one on the event, and now we can parallelize on cores, on GPUs, on nodes, on cluster, whatever we want. Everything will be okay. So just to remind you that, again, computing drives data storage, and you cannot have a random data storage and expect to have performances at the end. It's not possible. Or you are very lucky, maybe, but normally it's not possible. So that being said, let's talk a bit about CUDA. And CUDA, as Stephen Jones reminds us every year on the GTC, CUDA is an ecosystem. It's not a language, it's much more than this. So we'll talk about the language, of course, but not only. So in CUDA, we have the language, and we have some library to do some kernel development. So we have CUDA itself, we have Q++, and we have Kokkos, for example. We have other, of course, in other languages, but here we will try to focus on C++. On top of that, we have other libraries. like QBLAS, QLAPACK, QPBLAS, QSCALAPACK, Tensor, Sparse, QRound, and QFFT, to name a few. Because today I think there is something like 250 packages in the CUDA X ecosystem. So normally you should find what suits you for your computing. Then we have Thrust. So we'll talk again also a bit about that. And to compute with some I/O stuff, we have CuPyNumeric, Legate, and QDF, mainly for the Python developer. We have Magnum I/O for all the trickery on the communication with NVSHMEM and Nickel to have GPU to GPU communication in a large scale in a very efficient way. And we have GPU Direct for the GPU Direct storage, for example, where the GPU can read and write directly data on an NVMe, on a SSD, on a disk, hard disk, standard hard disk. And we have Nsight to do some profiling and to debug. And this is a lot of stuff. And the main point is it's an ecosystem, so you can mix together Thrust with CUDA, with Q++, with QClass, with BLAS, with a lot of stuff. And it's really nice also to be able to do that. So we will not do that in this presentation because I don't have time for that, but we will do that in the school because it's really powerful. So computing with CUDA, the first thing I think about when someone asked me to compute with CUDA, I said, okay, but can you express your computing with linear algebra first? Because if you do, you can use all the library I mentioned before, so you don't have to write your own CUDA kernel. And as Stefan or Georgi or Athena mentioned in their talk of the GTC, the best kernel is the one that you don't have to write. So if you want to do some calibration, for example, it's a broadcasting, so you can use library for that. If you want to do signal reduction, for example, I want to reduce all the rows of my matrix here to have one big column here, I can use matrix vector multiply. So I multiply by 1 because there is no way to reduce that in a proper way. So just for the naming convention, SGMV is single precision general matrix vector multiply. So I will use that a lot during this presentation. It's important to have that in mind. And for more complex computation, for example, if you want to do some momenta computation, we will do a classic matrix multiply with two matrices. So the event, for example, I want to project in another space, and the projection matrix I can use to extract momenta or whatever computation you want to do with your projection matrix. It's really generic. And this stands for single precision general matrix multiply. So we'll use that a lot again in this presentation. So first, if you can describe your computation with linear algebra, you will be able to use QBLAS, QLAPACK, lot of library for that. So you don't have to rewrite all the stuff yourself and to deal with all the weird details of the GPU implementation. And for example, to give you a really small backend example about that, you can do something like this. So for SGEM, for example, in QBLAS, you can say, okay, I want to do something really simple. And for me, I wanted to have a row-wise SGEM because practically all the BLAS are expressed in column-wise by default because it comes from Fortran. And once you have the habit to program and to compute in row-wise, and you have all the library in the world which are column-wise, and you want to try them, it's quite annoying. You have to do a bit of math, but it's possible. And here the example I use to call QBLAS SGEM, so with the QBLAS handle, because we do some trick with the GPU, so you don't have that for MKL, for example, or for LAPACK, but you do for QBLAS. And so I pack this little function inside a function that I define myself, so I know how it works. I can do a little unit test to be sure that my matrices are well ordered and there is no problem of transpose or stuff like that. It's important also to check this thing. And I can do the same for matrix vector multiplication. So it's really quite the same, in fact. And once I want to use them inside my software, I can do a type def. So you can do also some templating if you prefer, but as I know many people, especially scientists, do not really want to do template stuff because I assume they know someone who went too far with that. So level 0 of interface, you use a type def, you say, okay, my compute backend is a cubeless, and then we call cubeless SGM, GMV, stuff like this to create a handle. And you can use the MKL, you can use whatever library you want. If your boss comes into your office and says to you, okay, it's nice to have cubeless, but I don't have GPU, how do I do the computing? You say, okay, you change one line of code and that's it. It's always good to be able to do that. And if you can do that before you leave your office, it's even better. So now we will take a moment to remind ourselves about thread hierarchy. So we will start from the very bottom with the threads until the thread is executed on a core, and it will execute the computing kernel. So you will, once you write a kernel, you will be executed inside the thread. Then there is a warp. The warp is really managed by the hardware scheduler, so you cannot change it. You can see that as a vectorial register. So it's the hardware, you cannot change it. Generates 32 threads, and you have the guarantee that 2 threads in the same warp will be synchronous, and they will execute the same instruction at the same time. On top of that, we have the block. They are designed to be mapped on stream multiprocessor or computing unit, if you are talking the language of Intel or AMD, or even Vulkan. They contain from 2 to 4 warps, so 64, 128 cores, depending on the GPU. And here the execution is asynchronous, so you don't have the guarantee that 2 threads in the same block will be executed at the same time. At some point they will, and they will be synchronized, but not exactly at the same time. On top of that, we have clusters, so mainly for block communication, because GPUs are big since Hopper and CUDA 12. So Hopper is 132 stream multiprocessors, and Ampere it's 108. So a stream multiprocessor is less than 1% of the full GPU. So if you want to stop everyone to communicate between 2 blocks, it's a bit annoying. So that's why the cluster came out. And finally, we have the grid. So it's a full GPU, and you have the full Hopper and the full Ampere, depending on the number of cores that we want to use. And now we have the full Blackwell as well, with the 10,000 cores plus 10,000 cores. So that's for the thread hierarchy. And then once we execute, so a thread alone does not mean anything for GPU. We will talk about warp every time. Instruction will be loaded 2 by 2 and executed 2 by 2. And once we came onto a condition, all the thread will execute the condition at the same time to determine if the result is true or false. If the result is true, they will execute the then statement, and all the other will wait. And once it's done, the thread with the condition which is false will execute the else statement, and the other will wait because they're really polite. So to show you that once you have a statement, you will pay the 2 statements for your condition, not only the then or not only the else. If you have only one thread with a different path to the other, it will wait for everyone. So it's important also to remember that. That's why generally we told people that you don't want to put a lot of condition in your kernel because of that. And now we have to map data on the cores to be sure that the thread will be efficient. So the idea is to have the cores, and when we slice the data on top of the cores, or virtually, of course, and then we define the thread, and the thread pass through all the data at once, and we are very efficient in terms of memory usage. And to do that, we need to be efficient, and we need to know which thread to determine which how the data are mapped into the thread. And to that, we need to remember that the thread is on a core, the thread is in a block, the block is in a streaming multiprocessor, and the streaming multiprocessor, the block is in the grid, and the streaming multiprocessor is in the full GPU. And to know the address, kind of address of the thread and on the block, we have thread ID and the block ID, and we have 3 dimensions each, because a lot of problems are multidimensional for matrix multiplication, matrix product, etc. We need generally a lot of dimension. It's important also to have that in mind, to be efficient on the mapping, because the compiler will help you if you use several dimensions, and you have some limitation depending on the dimension, so you will also have to take that into account. So how can I determine the block size? So that's a bit tricky, but we have to pass through it. So let's talk about a Adana product, because of course it's why I'm at presentation, so for sure you will have an Adana product. And so I have 1000 elements, and I will try to split it into 10 blocks and see what's going on. If I do that, I will have the warp only, or again, in 32 threads, and all the blocks will be the same, but they will not be totally filled with a thread. Only 3 warp will be complete, and the 4th one will be only using only 4 threads, which is quite bad. And by doing that, we will use only 78% of the full GPU, which is bad. And if we change our strategy, we can say, okay, let's launch less block, 8, for example, of size 128. And if we do that, we have 7 blocks fully filled with threads. So all the warp are really well used. So 7 out of 8 is quite okay. And the last one will have a little kind of padding, if you want, with 32 threads for 3 warp, and the last one will be just less used because the life maybe has not always a power of 2 inside, or a multiple of 32 inside of the number of the elements. So we have to deal with that. And if we do that, we use 98% of the GPU, which is really quite better than the previous one. We can normally do better stuff. If, for example, we split the Adama product in a clever way, or we say, okay, let's compute more elements, because it could help also at some point. But if you are stuck with 100 elements, that's life. But you can also adapt your problem to say, okay, if I compute 1000 elements and if I compute 1024, it will be the same cost. So let's compute a bit more. Could be also a possibility. For the read and write, so we have the memory is divided into sectors, and one sector is 32 bytes. The cache line is 4 sectors, so 128 bytes. And if we have some data we want to access, so 4-byte element data on a warp, the warp will access 4 sectors at once, as we do in a vector register on a CPU. And if I want to access 8-byte element, the same, but with 8 sectors and not 4, and everything will be efficient. And this is really close to CPU vectorization, but the trick here is once you define your thread, you define only one thread here, and it's really easy to forget that the thread on the GPU does not behave the same way on the thread on the CPU. The thread on the CPU, you can do whatever you want. On a GPU, you have to think about your neighbors and do something coherent with your neighbors. If you use an injunction table, for example, and you jump across the memory randomly, you will kill your performances. Or you will transform your compute bound problem into a memory bound problem, and that's bad. So you have to, it's important to have that in mind also. Even if it's cool to say, okay, it's a thread, I can do whatever I want, but it's not true. So you have to remind that. And speaking of thread and on data access, the same for memory layout. So run read and run write is done sector by sector, so 32 bytes at a time. And if I have a structure of coefficient of 80 bytes, for example, so an array of structure, I have something like this in memory. So all the red blocks are my structure. And if for some reason I want to compute something with only U, for example, I will have some data access like this. So each thread of the warp will access a different sector. So I will kill my performances because I will fetch each time 32 bytes, but I will use only 4. So I increase my need for bandwidth, even if I don't need it. And I use a really small part of it. So again, I can transform my compute bound problem into a memory bound problem, which is bad. And to solve that, we do the same as we do on CPU, as Adrien said to you in the previous webinar. We want to use a structure of array. And by doing that, we will have lots of arrays here. And if I want to access the U table, all the elements are contiguous, all the access will be done once, and it will be very efficient. So it's important to do that and to split your data, your structure into tables. And the good point, as David said also before, once you have done that, to have a nice code running on your GPU, even on your CPU, it will be faster. So always good to know. And all the bytes are used, so everything is really efficient. So let's assume that we do that in a nice way. So let's program a bit now. So again, with another bar product, because what else? The core of the, it's not the core of the full school, but it's a good starting point. So it's element-wise operation, and to define that in CUDA, we'll create first our kernel like this, and we will start with global. The global statement here is to tell the compiler that we want to execute this kernel on the device or on the host. You can force it with device and host the same way it's written here, if you want to be sure that your kernel is executed at the place that you want. But if you do some global, the compiler will handle that for you. And then, as I said before, we have to have a way to say, okay, inside the thread in this kernel, how I know which data I want to treat. And this is about the thread position. So it's in one-dimensional example, so it's really simple. So we have the block ID.x, so to get the index of the current block with the current thread in it on the x-axis of the full grid. Then we have the dimension of the block on the x-axis. So because all the blocks have the same dimension inside the computing on a GPU. And then we had the position of the thread inside the block. So there is no question about warp or stuff like that. It's handled for you, but you have to take that account also. If you have some random here or injection table here, you will kill your performances. And here I access all the data. So as I said before, I can stack my data on top of each other. I pass through my data with my thread, and everything will be efficient. So this kernel is quite simple, but now we have to start it. And to launch it, we need to define this kind of function. So first we have to allocate some data on the GPU, otherwise CUDA will complain. And once we allocate, we think about to free the memory at the same time, so we avoid mistake and we avoid memory leaks. If you want to call a lot of time your kernel, it's better to out these two parts of this function because as Sébastien said before on his memory webinar, it's expensive to allocate even on the GPU. So if you can avoid that, it's better. Then we can transfer data on the GPU, on the device, if we use the proper word for that. So with the CUDA memcopy host to device statement here. And then we can get back our result with the CUDA memcopy device to host here. And it's not done yet because, okay, but we have to determine the size of the block and of the grid. And here it's a little piece of code to do that for one-dimensional block and grid. So for a really, really simple computation here, we will do that in 2 dimensions, of course, for the grayscale in the school. And you always have to pass through it once you want to compute some CUDA. And the point is, you cannot do whatever you want to do because you have a maximum number of threads you can have per block, and you have a maximum number of threads you can have on the grid for the x-axis and for the y-axis and for the z-axis, and they don't have always the same value, so you have to take care of that. You have a global maximum number of threads per block also. You have to take that into account. This is a really simple example, but you have a lot of things to do to be sure that you don't have any problem. And you can notice also the Philip CUDA check file. So it's a little macro. I will detail that into the school, because each time you call a CUDA function, you can have an error. And once you get the pointer of the error and you do that yourself, but it's quite heavy, or you put that into a little macro to do that for you and to get the proper error with the proper line. So we will do that also in the school, because you are using a different device, an accelerator, so a lot of things could go wrong, and you want to know that if there is the one problem, you want to know that immediately. So it's important to deal with that. And that, in fact, a big part of the development. Once you develop a kernel, you want to be sure that if there is a problem, you will know it as soon as possible. And once you do everything, now we can start our kernel. We can load the kernel with the famous triple chevron here to pass the dimension of the grid and the dimension of the block, and everything will start on the GPU at some point in a synchronized way, because CUDA memcopy, they are blocked. They will be blocked. We'll do that also with we can synchronize and do some in-synchronize call. We'll see that at the school. I don't have time for this webinar, otherwise it will be really too long, but we will do that also at the school. And to give you the full implementation, we have something like this. So it's not that bad once you know how to do it, but yeah, you have to think about everything, and maybe out the free and the malloc if you want to call this guy a lot of time. So if I do that, I can check my performances. So here in purple, you have the performance with the data transfer, and if green, you have the performance without the data transfer. So if I have already my computation, my data ready on my GPU, and I check the computation here I have on my GPU. And so basically we have here once we have enough data to treat, we are optimal. If we don't have enough data, we will be dominated by the start of the kernel and the little transfer that we have to do also here. And here the start of the kernel costs quite a lot, in fact. And the point is, generally when I start a kernel, I start with the monitoring before using Insight or other stuff. I start with the monitoring. If I have enough element to compute, the monitoring will be happy and say to me, okay, you are using the GPU at 100%. Okay, nice. If I use less data, it will say, okay, 97%. Not that bad, but quite okay. Here it will say 60%. Honestly, I'm not sure I reached 60% in that computing regarding the time and regarding the machine I use. Maybe it's a bit too much. Maybe it's 40%. Here it tell me that it's 22%, but I think it's less than 5%. The problem is, once you are using the monitoring is a bit optimistic. And if you say the monitoring is telling me that I'm 60% of the usage on my GPU, it's wrong. Unfortunately, it's wrong. If you are using Insight, it will say to you, no, it's not 60% at all. It's way less than 60%. So 100% is nice. Normally, the should be okay. If it's less, maybe it could be a problem of measure, because the monitoring will sample every second or every 2 seconds the usage of the GPU. So if your kernel is really, really short, maybe you will have some problem to have nice usage. So yeah, you always want to criticize the measurements you have with your monitoring, because generally it's quite optimistic. So don't be fooled by the monitoring. So I can do the same for thrust. So it will be quite simple. So it's still an element-wise operation. I can do it like this. So here, straightforward, I can initialize my vector, so host vector. So they belong to the host. And then I do a little transfer. So this is really elegant. You have a device vector and you copy your data from your host vector to your device vector, and you have a transfer. So you don't have to worry about the CUDA mem copy and the pointer on the void star and all this stuff. It's really, really elegant. Then you call the transform, and the transform is quite the same as std transform, as I mentioned in the C CPU part. But here you have host and device also to say, as before in CUDA. You can execute your kernel in host or on the device. And here it's the same, but it's not really a kernel right now. It will be a kernel at the end of the compilation, but now it's a lambda. So as David said, for the prerequisite of the lecture, if you are not afraid by this kind of lambda, normally should be okay. We will not do much more trickery inside C++ 20 or 17 in the lecture. The point is to use that in a really efficient way. So normally, if you are not afraid by this, or you say it's a bit weird, but you understand what's going on here, normally should be okay for the lecture, no problem with that. And finally, we can get our result back. So we copy the device vector inside the host vector. So with the prefix d underscore and h underscore. So it's a little trick that many of you, I think, use to be sure that you know which data belongs to which device on host. So to be sure that you don't miss and mix the information. And that's it. And the full correction is here. So it's really, really simple to use. And the point is, now I use host vector and device vector because I like to explicit if data on the vector on the device or on the host. I want to really be sure that I think I do what I think I am supposed to do. But you can use now first universal vector, and it really manages that for you. It's the same of the unified vector, the unified memory vector David told you about SYCL. It's the same idea here. And so you can allocate your data inside your host, inside your device, and once you use them in the host of the device, you will have an automatic transfer done for you under the hood. So you can also change it to have a unified way to express your computation. So right now we told about CUDA, NVCC to compile CUDA and thrust. In the HPC SDK, we have also NVC++, and it's time to talk about NVC++. So NVC++, as I said, since 2020, you can use in C++17 stdpar equals GPU to compile directly on the GPU and to execute directly on the GPU without a single line of thrust or of CUDA in general. So how can we do that? So again, with an Adama product, so we can compare. So it's an element-wise operation. In classical C++, we can write it this way with a classical for loop. And again, we don't need this explicit order because we don't have back dependency. So the ordering does not matter here. So why having an ordering? So we can use the STD transform from a long time ago, but nobody cares because it's really heavy to use it. But the point is, in C++17 and C++20, we have an execution policy, and you can tell the compiler that you want to execute it in sequential mode, so the classical for loop, in non-sequential mode, so potentially vectorized or reordered, for example, parallelize for TBB, for example, and parunsec for the GPU computing, and par also for the GPU computing. Depending on the kind of GPU you want to use, you have to use different flag at this part. And with our Adama product, so we can compile with CMake and say to CMake, okay, we have CC, so we export CMake C compiler with path to GCC, and the same CMake CXX compiler or CXX variable to give a path to NVC++, especially if you use the HPC SDK, you have something in OPT, NVIDIA, Linux, stuff like that. So it's to have a nice path, it's quite nice. And if you want to compute on a CPU, you say stdpar equals CPU, and that's it. And it will use TBB under the hood, as all the compiler I know, in fact. And you don't want to forget to link with TBB, otherwise you will have a linking error. So quite annoying, but you can get used to. And for the GPU part, you can say stdpar equal GPU, and you will compile with GPU, and thrust will be used under the hood. And on the contrary here, you don't want to link to any CUDA specific library. Otherwise, it will compile, but we will have an error on the execution. So let NVC++ do the work for you, and it will be nice. So it's quite annoying the first time because you say, yeah, but give you the CUDA library, please. But no, you don't want to give any hint to NVC++. It will under that for you, and everything will be nice. A main point on this is you want to avoid static allocation, because NVC++ needs a guarantee that all the pointer can live on the CPU or on the GPU, and for static allocation, it's not possible. So you want to remove all the static allocation of your software, and it's easy to forget about one static allocation because it's really nice to have a static allocation to allocate a table or something like that really quickly, or once you have a pattern which is repeated, you want to do that, or a really small matrix or something like this. And once you will execute it, you will have an error, and you have to figure out, okay, there is some static allocation somewhere, I want to find them. And for example, for the school and for what we do in production and on the analysis that I'm working on, we use HDF5, and HDF5 has a lot of static allocation in it, so you don't want to compile HDF5 with the stdpar GPU option with NVC++, so you want to split this part into a dedicated library, compile with NVC++ without the stdpar flag, or with G++, for example, or Clang++, and use it as a dependency, and you don't want to touch it with NVC++, otherwise it will complain and say, okay, but I have a lot of static allocation here, I can do nothing with that. So again, a lot of design to avoid this kind of problem. But we will see that in detail in the school because it's important. So about memory management, there is some trickery because once I do a stud transform, I don't explicitly say, okay, my data are on the GPU, are on the CPU, so what's going on? So classically in CUDA, as I mentioned before, or in Thrust also, as I mentioned before, you have data you want to access on the RAM for the CPU, and you have to copy the data on the memory of the GPU and access them later. And everything is nice. And everyone at some point forget to do the copy, and you have an error, and that's life. You have to deal with the CUDA error and say, okay, I have a problem. I cannot access this pointer. What? Okay, I forgot to do the copy. Okay. Since 2020 and NVC++ and NV also, we have unified memory. And unified memory means that you have data on the RAM for the CPU, and once you want to access the pointer on the GPU, there is still an error, but the driver catches the error and does a copy for you. So everything is okay under the hood, but there is some stuff going on to fix the data which are missing. So it's done automatically. So it's a kind of software unified memory as to opposition with the hardware unified memory that we get in Grasshopper, Blackwell, for example. Here it's really a software point. And to prove that to you, we will have a look into the Insight, the profiling of the Adama product here. So we recognize Insight with all the CUDA activity on the hardware, and some thread activity here, memory activity here, CUDA API and CPU stuff here. And we'll zoom a bit here, and you will see, okay, but on the memory side, we have a page fault host to device transfer. That's the error I mentioned before. So there is an error. You try to access data, but the data are not on the GPU. And then there is a speculative prefetch host to device transfer. So the driver told him, okay, data are missing. So they are supposed to be accessed on the device. So I need to get the data from the host to the device and do computing, to make the computing okay with that. So as you see in my computation, I have a lot of this because it's a big. I think I have 500 million elements, something like that, or maybe a bit more in the example. So we have a lot of transfer to do. And the point is, as David mentioned also in his SYCL presentation, here the driver is really smart. It's really nice to have this. But if you know for sure you will transfer a lot of data at the same time, it's better to do it yourself. And to help with Thrust, for example, to say, okay, I want really to transfer this bunch of data at once and do something with it. Here, it's better if you have not a small amount of data, because you need to have several kilobytes or hundreds of kilobytes to transfer to be efficient. But if you have really too large amount of data, it will be less efficient than if you are using a CUDA memcopy explicitly or a copy host to device with Thrust. So if you have a problem in performances, you have to profile, and maybe it's a problem you will have to fix. And of course, we recognize Thrust here. So it's not a Thrust transform, because at the end of the day, the Thrust transform is calling a lot of kernel here with the Thrust API, a cube API here with the kernel agent, etc., and the parallel I don't remember what. So the point is, this comes from your transform that we call the std transform of the example calls the Thrust transform, and which call this horrible function here. Now it's we have some update because we have also NVTX in Insight, so you can also do some NVTX stuff, but I don't have time for that for this webinar. So we'll move on a bit. And so now to conclude this part as not quite the same size I did for the last time on the CPU, but to remind you that here it's about triadic. So with stud transform, with thrust transform, it's about triadic, or for each also if you want. So a triadic is C equals X plus Y, for example. So you have one operand, two operand, one operator, and you have a result. And if you want to do a quadratic computation, so X plus Y times Z, for example, the standard way to do it, if you want to do some GPU computation after that, so you can do a classic C++ like this, but you cannot on a GPU. So you want to use a stud transform here with a vector of index to handle that for you. For the vectorization, as I mentioned before in the CPU part, you want to have vector Y and Z to be std vectors, otherwise the compiler will not vectorize. But as I mentioned before also, the compiler will be completely lost in the optimization, and the performances, even if you vectorize, will be horrible. So if you pass a pointer, it will be okay. And the point is, it works well on the GPU. And at that point, you will have to do a copy because of the data. You need to copy data from the host to the device. Even if the driver does that for you, you need a copy at some point. And another thing is about the syntax. Once you use the lambda here with NVC++, you are obliged to use an equal. If you are not using equal but reference, the NVC++ will yell at you and say, no, you cannot use a reference because I want to be able to copy data from the host to the device and from the device to the host. So you need to catch all the variables by copy and not by reference. Otherwise, the compiler will complain. So it's not really elegant because we need an extra table. But on the other hand, it's quite nice because it's really close to CUDA kernel computation. So once you define a CUDA kernel, you want to have the index of the data you want to deal with. And here I have my lambda, and I have the index of the data I want to deal with. So yeah, it's what I did for the grayscale. I implement my grayscale in CUDA, and then I copy paste the kernel inside my lambda, and that's it. It's done practically. So it's quite nice also to have that, even if it's not really elegant to allocate a vector of index just for that. But it will be better at some point normally, and normally I have a bit of time to show you the future with C++33, for example. So to do, for example, here a transposition without having to allocate a lot of indexes, we can use views iota. So views and iota, so stud ranges use iota. So to have a range of, as we can do in Rust, for example, a range of value from 0 to n or from 0 to m, depending on the value that we have here. So with mdspan also you can use mdspan. You can use an mdspan also with libc++, with CUDA stud mdspan and CUDA stud span, for example. So it's nice also to use. It's a bit horrible to compile, but it's nice also to use. And then we can define the for each and pass the parentsec execution policy to be sure that we will use the GPU well. We pass the view of all the indexes we want to treat. And the auto here is a tuple. And we can unpack the tuple and say we have I and j indexes. So imagine we have a CUDA kernel and we have x-axis and y-axis to do some computation regarding a matrix or image or something like that. So it's quite also nice because you can get back the multiple indexes you can have with CUDA. So it's nice also if you want to move from classic CUDA kernel to this. And so it's multidimensional, it's nice. There is no allocation also. It's quite okay. And we can use that for broadcasting, for example, but we can do better for broadcasting, because broadcasting is this kind of computation and a Nadamar product broadcast again. And if you want to do that, you can extend the vector of B with repeat. So repeat will get the vector of B and duplicate it in a view, not really duplicate it, but in a view, we'll have a vector of vector B here. And with the join, we will put all the different instances together to have a long vector in an infinite size, because the repeat do not have boundaries here. Otherwise, it does not compile, of course. And if we do that, we can manage to compute A times B without worrying about the boundaries of B. But this is not vectorized yet. This is not parallelized yet. And for now, there is only G++13 and a bit of G++14 also, which are capable to compile this. It's not possible to do that with NVC++. It's not possible to do that with deeply C++. And it's not possible to do that with Clang also. So we have to wait a bit. And speaking of C++ evolution, so with C++17, it's quite nice because we have a lot of stuff to move between the CPU and the GPU. We have the stud transform, stud for each, etc. A lot of algorithms which are available, so it's nice. Basically, all the algorithms you have in Trust, you can have them in the stud namespace, so nice. C++20, it's quite okay, even if there is no everything, but you have some stuff, even if officially NVC++ does not support C++20, we will do a lot of C++20 in the school. It will work, no problem. Not the case for NVCC. NVCC, you don't want to use C++20 with NVCC. C++17 is better. And C++23 will have, as I mentioned to you, views and ranges to avoid the index allocation and to have more C++-ish way to do stuff. And finally, C++26, we mentioned that several times with all the linear algebra interface that will be really helpful for the computing. And to conclude this presentation, so we have good performances on GPU with CUDA, with NVCC, and with NVC++, with C++17 and C++20. So I tested that with HPC SDK 24/7. I'm currently upgrading to the very last one here, so 24.3 normally. But I need to get some space on my laptop to do that. But it will be ready for the school, no problem. So the compiler is really, NVC++ is really powerful and really easy to use, even maybe too much, because as I said, you don't want to explicitly link to CUDA library as you do for NVCC, for example. And so it could be a bit disappointed at the very beginning because you try and it's not working and you say, okay, but how should I fix that? And in fact, you do nothing and it's okay. So quite nice, but yeah, you have to take that account. It's, as I said before, also CUDA, it's an ecosystem, so you can use CUDA visible devices for all I mentioned before. It will work on NVC++, on NVCC, on Trust. Everything will be okay, so no problem. You have to avoid static allocation to be sure that everything will compile well and will be executed well. Otherwise, you will have some error. And it's quite tedious to find the problem inside your code, especially if you have a lot of code, a big code base. So it's complex, but you have to pass through it if you want to do it. It's really, really powerful and nice to use. And about the little warning at the end, so as you know, there is no more support for K80. There is no support also for NVC++. You cannot use it before compatibility 6, so before Pascal, so Maxwell and Kepler, you cannot use it. It's not possible, but since Pascal, it's possible. So Pascal, Turing, Volta, Ampere, Hopper, Blackwell, okay, no problem. For NVCC, compute capability is 3.5 with the version I mentioned here, so 24/7. So no KAT in CUDA 12, no, not possible. Even if we still have some KAT which are working well in the cluster we use, but not with the last driver, unfortunately. But we can do a lot of things with them too, especially to teach. It's nice. And to do that, we need to save binaries because at some point maybe they will remove the binary on the everything, so we have to take that account also. And thanks for your attention. I hope I'm on time. Yeah, practically. If you have some question, I will be glad to answer them. Does Threads support anything but CUDA hardware? I think yes. I never tried Thrust in other GPUs, but I'm not sure it will be compliant with that. In fact, you can see Thrust as a kind of it's a backend, so you can see that as a backend, the same that you use the CUDA backend for SYCL or the Intel backend. That's a backend. So yeah, I think NVIDIA Thrust is okay only for NVIDIA GPU, but it's a part. Question from David. With NVC++, no way to get the stud part executed on GPU? Yes, but it depends. Okay, let's go into the details. It depends of your GPU. If you do stud par with, I think it's A100, you will use your A100, or maybe it's with Turing, maybe it's with, on the T4 I had this issue, but you define stud par, so stud par and not stud par unsec, and you will use the GPU, but for some reason, you will use the GPU with one thread. So of course it will be really, really slow. And I think when I did some test on Pascal, it was the opposite. If you compile with parunsec, it will say to you, oh, it's not possible. Parunsec is not supported on Pascal, so you have to use studpar and not studparunsec. So yeah, you have to check that. So it's possible, but depending on the GPU, depending on the flag, depending on what you want to do, you will have different behavior. So you have to check that definitely at the beginning. So another question from David. Object files made with NVC++ are compatible with object files made with G++ and Clang++. I didn't check with this order. Usually I compile with extra libraries with Clang++ or G++, and I use them inside the projects that I compile with NVC++. But if it works in this sense, maybe I don't see what it should not in the other way. We have to try, but no, it should be quite okay. Question from Guillaume. If I understand well, you can import G++ compile library in your program, compile with NVC++ without issue. Yeah. I do that on the production even if the GPU backend is not used in production now, but we will use it. And for the school, yeah, we do that also for the school. It's really, really powerful. No problem. Yeah. Maybe it depends on the version you use. For the version I used, I didn't have some problem. If you want to be sure and use maybe NVC++ for everything, you can say I use NVC++ for everything, but I use the studpar equal GPU only for the GPU compute and not for the rest. Even if I think to have the proper linking on the main, you have to specify it. If I remember well, the trickery I had to do last year for the lecture. But yeah, you have to be sure that the flag is okay, because NVC++ we also do the linking for you. And you have to specify the studpar equal GPU for the linking. So it's a bit annoying. You have to be aware of that, but it's possible. Another question from Guillaume: to which extent can performance be affected by these new interfaces using transform and NVC++ compared with refining by hand, block, and thread? In fact, it's quite funny because I do the opposite. So the really good part with thrust and with stud transform with NVC++ is you will get practically every time the optimal size of the block and of the thread, the number of thread per block and the number of block for the grid. Normally, every time once I ask NSIGHT, because NSIGHT will give you the occupancy of the GPU and the efficiency of the kernel, every time I ask NVC++ or thrust, they give you better results than what I can do myself, even with a lot of effort. So generally, it's better. On the data transfer part, as I said, if you have a lot of data to transfer at once, maybe it's better to do the transfer yourself. But on the computing part, on the kernel, determine the number of threads per block and the number of blocks in the grid. Honestly, it's really, really good for what I use every day. The computing is really good. Here I showed you a really simple example of how I'm supposed to compute the grid size and the block size with a few elements and few information in one dimension. Of course, thrust and NVC++ will do that for all the dimension you want to use, even if mainly they will use the first dimension because they don't really know the size of a problem, but the result is really, really good. So generally, I inspired from what Thrust is using as a size, even if it's generally multiple of 256 instead of 128, because generally 128 you are suboptimal in real GPU or in recent GPU, for example, Ampere, A100, stuff like that, or even more recent GPU. So you don't want to have less than 256 thread per block. Even if you want to increase the parallelism at some point, you will have to. But otherwise, for recent architecture, we don't have enough warp in flight at the same time. So that's another problem to take into account. So question from Kenneth: is it possible to allocate data directly on the device? Yes, you can. It depends on what you want to use, but if you use Thrust, you can. If you use CUDA, you can. And if you use ST transform, normally there is a lazy allocation. So yeah, I did not mention that on the NSIGHT profile. I will on the school. So here, if I transfer data of my two vectors x and y on my device, I will add the prefetch, the speculative prefetch, as I mentioned to you. But if we have a look to the result, which is not used at first on the CPU but on the GPU, there will be a lazy allocation directly on the GPU because it's a first touch, as Sébastien mentioned before on the memory webinar. It's the same for the GPU. So there is a lazy allocation, and if you declare your vector on the host, but you are using it the first touch on the GPU, it will be allocated directly on the GPU. So it's a kind of a way to do that, but if you want to allocate it and fill it with some values, unfortunately, I'm afraid that it will allocate it on the CPU first and then on GPU. Or what you can do is to use a transform or a for each to allocate your vector with an execution policy parallel unsec, and it will do the first touch on the GPU and allocate it right on the GPU without the transfer. So you have to comment your code if you do that, because it's not it's under the hood, so it's quite hidden. So, but you can do that. You can do that, and normally we will do that in the example. If I remember well, I have to pass through all my example, but normally we will do that. So another question from Kenneth related to the CUDA ecosystem. What about unified memory on Apple devices? I don't have Apple at all. no smartphone, no laptop, nothing like that. So I don't know. Normally it's quite powerful, but as David said before, Apple seems to live in the Apple world and not really talking to the other actors. So not sure. Normally it's supposed to be quite efficient, but I don't know. I don't practice this stuff, so normally should be quite efficient with M1 and 2 F3 stuff with the shared memory, the physical shared memory, as we have in Grasshopper, for example. But yeah, I don't use it, so I don't know. So from Fangatlo, are these algorithm in stud synchronous or in synchronous? It's a good question. They are synchronous normally, even if there is some trickery with the memory management. But if you are profiling them, you will see that we use the default stream, so the stream 7, which is the default one. So yeah, in fact, yeah, once you are synchronous, you are using only one stream, the default one. So we are using the default stream. In the news we have on the GTC, I don't want to spoil too much, but in the news we have on the GTC a few weeks ago, we have news to use to pass streams inside the stud transform and for each and etc. In thrust and in thrust transform and stud transform also. So it's coming. I didn't check that because I have to upgrade my compiler, my HPC SDK for that, but should be possible at some point. Maybe it's not working that yet, or maybe it's not compiling yet, but it's on the pipe. It will be possible at some point. A question from Guillaume. Thanks. It's much better to use the generic library than to use the architecture-specific tool code. Yeah, it's definitely much better to use all these libraries. I encourage you to use these libraries. In fact, the point is not a question to be lazy; it's a question to be maintainable and to open the door for newcomer. So, for example, if you write a really specific CUDA kernel, kind of a ninja programmer programming level, you cannot have an internship for that. You cannot have a PhD for that, even if it's a PhD on physics and just to do some simulation or whatever. Don't want to be bothered with that. If you are using QBLAS or MKL or LAPACK and you do a matrix product, everybody can understand the matrix product, whatever the stuff behind it. So it will be definitely much easier to see. And again, you don't have to sign with your blood. I want to use QBLAS. I want to use MKL. I want to use LAPACK. Use whatever you want. If you want to change, you just have to rewrite a really small backend, really simple. And you can start to develop, as David mentioned, in the cycle. The point of the cycle is to have a standard interface to do some computing on the GPU. You can do the same at your level with some BLAS. I don't really know why it's not the case. Normally, we should have a library right now, but I think it will be on the C++26 standard, but at some point we will have this. But for now, you can use the little trick I showed you in this presentation to just create your own backend, and once the real backend will be ready, you can move to it. But you don't have to be stuck and to put QBLAS everywhere, and then someone told you, yeah, but if you want to do QBLAS, it's nice, but CutLAS is better for half precision on Hopper, whatever, or mixed precision on Blackwell, for example. And you say, I have QBLAS everywhere. How do I do that? You can change the backend and say, okay, let's use CutLAS. So yeah, it's always nice to have a backend. So question from Jeremy. Thrust was almost discontinued by NVIDIA 8 years ago. Aren't you worried to rely on it? Thrust is always maintained. Maybe they moved the repository, but Thrust is up to date and has a lot of improvement. In fact, yeah, I have a lot of things to show you on the summary of the GTC about Thrust. There is a lot of activity on Thrust, so there is no problem to use Thrust. So maybe it's the same trick as libc++. Maybe they changed the repository, so you it seems like the repository is stuck, but it's not, or maybe it's not. Maybe it's less open source than before. It's also possible. For the same for NVComp, but yeah, we will discuss that for the summary of the GTC. But some projects are not open source anymore, and some are now, but they were not before. There are some movement, but yeah, Thrust is really powerful. Okay, thank you very much for introducing the webinar. Question from Christina. Yes, it's very important to use generic linear algebra libraries, and so very important to be generic on top of that. Yeah, to be able to replace instance LAPACK with SKLAPACK if needed. Yeah, it's that's a bit of bigger trickery of the school. We told you that we speak about high performance computing, but in fact we speak a lot about design, because the design makes you to be sure that you can maintain your code, you can add some people in it, you can try also, because for example what we do in the software, I had an internship last year to do some tests with a new backend, new GPU backend. So we already had a CUDA backend, and the point was, okay, let's try to play with to transform and for each and whatever, and see what we can do to have a generic backend CPU plus GPU. The interface, in fact, yeah. So recently I had an interview of a student, and told me, yeah, what is the most important thing you learn on your whole HPC career? And definitely it's the design. It's really the design, the most important stuff. It's the design which define if you will get stuck at some point or not. If the design will tell you if you will be portable or not, because at the end of the day, if your boss is coming to your office and say to you, okay, it's nice to have this stuff in CUDA or in AMD or whatever, how I'm supposed to use it on CPU only or on another GPU or whatever, and you say, okay, it's maybe 3 months of work instead of I change the type def and that's it, there will be some problem. So, and if you can change the type def before I leave your office, it's even better. So yeah, thank you for the webinar. Thank you, Christina. It was a long, very dense webinar. I did not have time to cover the streams, the CUDA streams, CUDA graphs, stuff like that. I hope we'll have time. CUDA stream, definitely we will do that on the school. So we have a lot of things to deal with. So question for Matt. I used Thrust many years ago. And at this time, if I remember well, it was almost as fast as low-level libraries, but the advantage is that you did not have burning yourself with kernel and the low-level stuff. Yes, you don't have to. You still have to think about your design and to think about your data layout and to think about how you want to split your computation. You still have to do that, but you don't have to be bothered with okay, how much block, how much threads, how I do that. But you still have to have a well-designed software. But yeah, it's really, really powerful to stress. And even for a POC, you want to do a proof of concept of something. You don't want to be bothered with a full CUDA stack, just a little check. You will stress to compile with NVC++. You have 15 lines of check. It's okay. Oh, it's a good idea. We have all the other stuff coming out with dot transform and with a thrust transform in the GTC. If you are using Hopper, for example, so as I mentioned before, in Hopper you have TMA, so the transfer memory acceleration. Once a part of the device will handle the prefetch of the data for the thread itself. So the thread does not have to compute the address and to fetch the data. The piece will do that for you. A piece of the hardware will do that for you. You can wrap your lambda inside another function, which I don't remember because the name is that big. But you can do that to tell the compiler that you want to use a TMA. So you will have even faster access to the data if you use that inside your lambda, so inside Thrust or inside stud transform. So it's a part of the new feature I will present to you the 12th of June. Yeah, Matti, yeah, you have to organize well the structure of data. That's the main point. Maybe I didn't mention that, but to give you an overview of that, when I was in PhD, the first thing I did for the optimization of a really old analysis of Cherenkov telescope was to change data format. And by doing that, I get a speed up of 40, just by changing data format, not by vectorizing, changing the compilation option, stuff like that, just the data format. And everything after that was about vectorizing, data prefetching, make sure that your computing is not redundant, stuff like that. And then we can build on top of that. But yeah, 40 just from one crappy data format to a nice organized data format. So yeah, that's really important. That's the core of your design normally. The data format is really important. Okay, thank you. thank you, Mattei. So maybe we can wrap it up if you don't have more questions. Thank you for attending this webinar. Hope you learned some stuff and you want to do some GPUification with some computing. So we will address a lot of stuff in the lecture. So no problem. So yeah, thank you. Thank you. So yeah, I think it's time to wrap it up. So thank you for attending this webinar. So next week we will continue the trickery on C++20 with Eve. So the library will be presented by Joel. So if you don't know Joel, you really want to see that because it will be a really nice webinar. So about Eve, so it will be computing on CPU, but with a well abstracted library for computing. So kind of step transform, etc., but for really mathematic point of view and computing point of view. So don't miss this webinar next week. Thank you, Stefan, for the nice comments. So there is a lot of thank you. So as always, once it's time with a lot of thanks in the chat, it's time to stop. So thank you everyone for attending the webinar and see you next week. Bye.